So in this activity, we're thinking of a vector space of polynomial functions. And they don't actually supply a degree limitation for these polynomials. These can be polynomial functions of any degree at all. And the function here is the function which takes one polynomial as its input, and it spits out as output the derivative of the polynomial that it was given. So we're thinking of the derivative from calculus as though it's a function. It takes in a polynomial, and it spits out a polynomial which is the derivative of the one that it was given. So if you give this function d x squared, it's going to spit out 2x. If you give it x plus 1, it's going to spit out the constant polynomial 1, and so on. Right? So the derivative here is being conceived of as a function operating on polynomials and spitting out polynomials as output. And one of the first things that we learn in calculus about the derivative is that the derivative of the sum of two functions f and g is the same thing as the sum of the derivatives of f and g. Right? The derivative of x squared plus x is the same as the derivative of x squared plus the derivative of x. We also learned that if c is a scalar, a constant, if I multiply a constant by a function and then take the derivative, I get the same result as if I took the derivative of the function first and then multiplied by the scalar afterwards. So what's our conclusion here? Like what can we say for sure is true about the derivative as a function on the space of polynomials? Can we conclude that the polynomials are not a vector space? Can we conclude that the derivative is a linear map? Or do we conclude that the derivative is not a linear map? What do you think? The derivative is a linear transformation. So that's something your calculus teachers won't tell you. I just finished teaching a multivariable calculus, and we didn't pay much attention to this. I don't think we did at all, really. Although technically, in multivariable, we saw the gradient of a multivariable function. The gradient actually can be thought of as a linear transformation. We did things like take the gradient's dot product with various things, and that's just like using the gradient like it's a matrix, which represents a linear transformation, because that's exactly what we were doing in secret, right, when we do that in multivariable. So yeah, the derivative is a linear transformation from the space of differentiable functions to the space of differentiable functions. Here it was just polynomials because those are the ones that we know how to work with, but in general, because of this linearity properties of the derivative, that's what we call these in a calculus book, the derivative is a linear map.